Now, good morning, everyone. Last lecture we study about the electrical system. Now, in this lecture we study about the translational mechanical system. It is already shown that electrical networks can be modeled by the transfer function that algebraically relates the Laplace transform of output to the Laplace transform of input that we have discussed in the last lecture. Now the same thing we can do for the mechanical systems. In this section we concentrate on the translational mechanical system, and in the next lecture we can extend this to the rotational mechanical system. So the importance of this is that the electrical system can be interfaced to the mechanical system by using the transfer function. Let us suppose that we have the transfer function of the electrical system and this is the transfer function of the mechanical system, that these can both be cascaded or interfaced, and it has it finds the application in electromechanical systems. Like we in the previous lecture we discussed about the resistor, capacitor and the inductor. In this case we take some of the important properties of the spring, then viscous damper and the mass, and write their equations. So first equation is the force velocity equation between this that spring. Then we have the force displacement, that displacement is directly proportional to the force in this case, and second is that viscous damper. In this case this force is directly proportional to the velocity, and velocity can be represented by dx by dt, and similarly mass force equals to ma, that is mass into acceleration, and it can be represented by this, and this column represents the the Laplace transform of Laplace transform that we have already discussed for this integrated function, and this is a simple function and this is the differential function. Now first one shows that the force is related to the velocity by this relation. This is a force and this is velocity by the integral relation. That is force, this displacement x is directly proportional to force in this case, in case of spring. Then in case of the viscous damper, the force is equal to this constant Fv and dx by dt, that is rate of change of displacement, and the mass is equal to m into rate of change of velocity, that is force equal to ma in this case. Now the mechanical systems parallel the electric networks to such an extent that there are analogies between the electrical and the mechanical components and the variables. Mechanical system like electrical networks has three passive linear components. Two of them are the spring, that is the first one, and the mass and the energy storage element. That is spring first and this mass, these are actually two energy storing elements, and this one viscous damper, it actually dissipates the energy. So these two energy storage elements, that is the spring and the mass, these are analogous to electrical storage elements, that is inductor and the capacitor, that is inductor and the capacitor. So the spring and the mass is analogous to inductor and the capacitor, and the energy dissipator is analogous to electrical resistance. So this is analogous to electrical resistance. So in this case you will see the K is the spring constant, Fv is actually coefficient of viscous friction, and m is mass in this case. Now take the force velocity column of this table, that is table 2.4, and the voltage current column of table 2.3 that we have discussed in the previous lecture, in case of electrical systems, we see that mechanical force is analogous to electrical voltage and mechanical velocity is analogous to electrical current. Also, if we compare the force displacement column of table 2.4 and the previous table 2.3 and its column voltage charge, it leads to the analogy between the mechanical displacement and electrical charge. We also see the spring is analogous to capacitor and mass is analogous to inductor, and this damper is analogous to resistor. Okay. The summing force is written in terms of velocity. If we write the summing forces in terms of the velocity, is analogous to the summing voltages written in terms of the current, and the resulting mechanical differential equations are analogous to the electrical, that is, are analogous to electrical differential equations. That is these are analogous to electrical differential equation. However, it is written in terms of displacement, then there is we cannot see any analogy between these two equations. So this is how we can relate these mechanical system and the electrical system. Now, another analogy can be drawn by comparing the force velocity column, this column of this table 2.4 with the current voltage column of 2.3 in the reverse order. Here the analogy is between the force and current and between the velocity and the voltage, that is force and current and velocity and the voltage. Also, spring in this case is analogous to inductor, which is opposite in the previous case, and viscous damper is analogous to resistor, and mass is analogous to capacitor. The summing forces, if written in terms of velocity, in this case is analogous to summing currents written in terms of voltage, and the resulting mechanical differential equation are actually analogous to the nodal equation. Now in the further lecture we will discuss this. Now to describe the mechanical system, we require only one differential equation, that is the equation of the motion. We will begin by assuming one certain positive direction of the motion. That is, we assumed one positive direction of the motion. Let us suppose F, force F. This assumed motion is similar to the current direction in case of electrical network. Using the assumed direction of positive motion, we draw a free body diagram. Free body diagram means that it represents all the forces that acts on the body either in the direction of the motion or opposite to it. Let us suppose the force is applied in this direction, and let us suppose that there is some spring which is tied to it, so it applies force in this direction. Okay, so first we draw the free body diagram. We place all the forces on that free body diagram, and then we use the Newton law to form the differential equation by summing all the forces which are acting on it. Whatever the force is acting on it, we sum all these forces and we get a differential equation. We assume the initial conditions are 0, and again, like we have done in case of this system, in case of electrical system, we take the Laplace transform and find out the result. Now let us take an example. Let us suppose that this is a system in which m is the mass, the force applied on it is F, and due to the force the displacement in this case is xt. So as you know, the force applied is F, so input in this case is F, and the displacement in this case is xt. So we have to find the transfer function x divided by xs divided by fs, that is output divided by the input. First of all, we start with this free body diagram. We draw the free body diagram as shown. This mass force acts on the mass in all the directions. So we assume the mass is traveling towards the right. Let us assume that this mass is traveling towards the right and the applied force points to the right. All other forces impedes the motion and acts in the opposite direction. That is, this one due to the spring, this one due to the viscous damper, and this due to the acceleration, okay. So it will also point towards the left. So we see that it is moving towards the right. So it has some force, it is moving towards the right, and all other acts as a deterrent to it. So Ft equal to kxt Fv, this one, and m d square xt divided by dt square. So if we get the differential equation of if we take in s domain, it is k xs Fvs xs, that is we have in this it is a differential, and this is the double differential, and we get fs. Finally we take the Laplace transform of both the sides and we get this equation. Since we want the ratio of xs, that is the displacement by f, so simply we get xs by fs is equals to 1 divided by ms square plus fvs plus k. So this is actually the transfer function, and this can be represented by inside the block, and on the left of the block there is the input, and on the right of the block there is output as shown there. That is, input in this case force, and the output in this case is displacement. So similar in the electrical case, we have simplified all the equations in that. Similarly, we can also simplify it. We can take it first the Laplace transform, and then we can make the equality of all the forces acting that we have done in the previous case. That is also one of the way to do it, to simplify the calculation without going into the these differentials and thus integrals. Now one more point, that many of the mechanical systems are similar to the multiple loop and multiple node electrical networks, where more than one simultaneous differential equation is required to describe the system. That is, if we have more than one loop, then we have two different equations for that. Now in the mechanical system, the number of equation of motion required is number of linearly independent motions. Now what do you mean by this linearly independent motion? Linearly independent implies that a point of motion in the system can still move if all other points of motion are held still. Another name for this is degrees of the freedom. Now, for example, let us suppose that we have two loops of the electrical network. Let us consider that we have in an electrical network we have the two loops. Okay. If we open the circuit, if we open the one loop, let us suppose that we open the one loop, then other current can still exist if there is the voltage source in that loop. That current can move in second if still there is the voltage source in that. Similarly, in case of the mechanical systems with 2 degrees of freedom, one point of motion can be held still while the other point of the motion moves under the influence of the applied force. If we held one still, but still second will move under the applied force, that means that it has the 2 degrees of freedom. Now the simple example of this, a system with the 2 degrees of freedom, we can discuss. That is, let us suppose that we have mass 1, then we have the mass 2. These are connected by the spring. Let us suppose it to be K2. Then it is connected by the damper. Let us suppose FV. Then we have spring K3 which is attached here, and here we have spring K1 which is attached here. So force applied, let us suppose, is Ft. Now force applied in this case is Ft and the displacement is Xt. Let it be F1 x1, and force applied in the second mass is F2 and x2. So this is an example of 2 degrees of freedom, that is system having 2 degrees of freedom. So in this case, in this system having the 2 degrees of the freedom, each mass can be moved in a horizontal direction while the other is still held still. So for that, 2 simultaneous differential equations are required to solve. Now we have covered the electrical and translational mechanical system. Now we are on the rotational mechanical system. Here we have the component, torque, angular velocity, torque, angular displacement, and the impedance. Now rotational mechanical system are handled the same way as the translational mechanical system, and in this case the torque replaces the force. In the previous case we had force, then now we had torque. Angular displacement replaced by translational displacement. The mechanical components for rotational system are same for the translational system, but only thing is that in this case there is rotation and not translation. Now in this case also, the mass in the previous case is replaced by inertia. The value of K, D and J, that is K, J, D and J are spring constant. K is actually spring constant, and D the coefficient of viscous friction, and J in this case is the moment of inertia. And it can be proceeded in the same way as the translational case, that is finding the Laplace transform in this case also. Now the concept of the degrees of the freedom is similar as in the previous case, but in this case we test a point of the motion by rotating it while holding all other points of motion. That is, the number of points of motion that can be rotated while all other points held still equals to the number of equation of motion as in the translational case. Now writing the equation for more than 1 degrees of freedom of this rotational system is similar to that of writing them for a translational system. The only difference is that the free body diagram consists of the torques rather than the forces in the translational case. Now we obtain these torques using the superposition. What we do, as in the previous case, we rotate the body while holding all other points still and place it on the free body diagram, all torques due to the body's own motion. Then holding the body still, we rotate the adjacent points of the motion one at a time and add the torques due to the adjacent motion to the free body diagram, and this process is repeated for each point of motion. So for each free body diagram that we obtain by keeping others still and taking one into consideration, we have one set of differential equations. Here is an example of electromechanical system that we have discussed, that is electrical system, then it is having transfer function, then cascaded with the mechanical system having some transfer function, and it can be represented by this, that is, there is some electrical system and then we have the mechanical system that is connected with the electrical system, and all the systems are having one transfer function, then we can analyze the system. Now in this lecture we will study about the electrical circuit. And so previously we will discuss about the electrical circuit analogues. We have pointed out the similarity between the equations resulting from the Kirchhoff's law of electrical systems and equation of motion in case of the mechanical. Now the variables of electric circuit behave exactly as analogous variables of mechanical system. In fact, if we convert the mechanical system into electrical networks before writing the equations, so it's a problem solving approach that we want to pursue, that we can easily compare these two and then we can find the analog, mechanical analog of the electrical. So the electric circuit that is analogous to system from another discipline is called the electric circuit analog. Analogues can be obtained by comparing the equations, that is differential equations of motion of the mechanical system, with either electrical mesh or the nodal analysis. Like let us suppose that we are considering some differential equation of electrical system, and then we are considering the differential equation of mechanical system, and we take this equation and find out the analogy between the two. Now when compared with the mesh equations, the electrical circuit is known as the series analog, and when it is compared with the nodal equations, then the resultant electrical circuit is called the parallel analog. As we have already discussed that the Kirchhoff mesh equation for the simple RLC circuit, it can be written as Ls plus R plus 1 by Cs, that is RLC circuit, into Is, which is equal to voltage Es. Now in case of the rotational mechanics, we have also found out this transfer function, that is Ms plus V plus K divided by S into Vs is equal to Fs. Now comparing these two equations, writing these two equations and then comparing these two equations, so after comparing we will see that mass is analogous to inductor in this case, viscous damper is analogous to resistor in this case, spring K, constant K, is analogous to capacitor in this case, applied force is analogous to the voltage source, and velocity is analogous to mesh current IT. Now this is an example for series analog system. Now let us consider a system in which these are in parallel. So we have to take into consideration the system where these are in parallel. Then using the Kirchhoff nodal equation we have to write for the parallel circuit, and we get Cs plus 1 by R plus 1 by Ls into Es, which is equal to Is. Now comparing it with the previous mechanical equation, that is, we can write the previous mechanical equation as Ms plus Fv plus K by S into Vs equals to Fs. Now for a parallel circuit, if we compare these two, then we get an idea that mass in this case is analogous to capacitor, viscous damper in this case is analogous to resistor, spring in this case is analogous to inductor, and applied force is analogous to the current source, and the voltage Vt in this case is analogous to node voltage in this case, that is Et. So this is actually the analogy with mechanical system with the electrical system, that is parallel and series. Now there is an example that we have to find the series in the parallel analog of mechanical system, that you have to do at your own hand. Now the series analogous of this mechanical system somewhat looks like this. The parallel analogous of this mechanical system looks like this. Now in the first chapter we have discussed about the antenna control system, that we have drawn the block diagram of that antenna control system that we have to control. In that case we have created a block diagram that how it works in all that aspects we have seen in that. Now after finding the transfer function associated all these rotational and these translational elements, we find the final transfer function diagram of that antenna control system that we have discussed. That is, in that it was previously it was the differential amplifier, then power amplifier, then it was the motor, then after the there is some translational this rotational mechanism is there, then we control the azimuthal angle. So you will see that this is schematic. In this schematic we have all the things which are available, that is we rotate it, and then differential amplifier will work, after that power amplifier will work, after that the motor will rotate, and it rotates the gears, and as a result this azimuthal angle is changed as per the requirement. And this is a feedback that we have also discussed, that is this feedback checked whether it is right or not. Now it is converted into schematic. This is our layout. This layout is converted into schematic. Now we have read about the translational and the rotational system. We have to find the transfer function of that. After finding the transfer function, we can this is the block diagram of whole of the equation, whole of that system, that it contains the potentiometer, it contains the preamplifier, then power amplifier, then motor and the load, and then gears, and then finally azimuthal angle is changed, and this potentiometer will take care of all the aspects that it is changing or not as per the requirement, and if it is not, then it will give an error signal to this. So this is the schematic how this can be done, that is antenna control system that we have discussed. So this is a very important topic today that we have discussed, that is translational part, then we have the rotational part, then analogy, and then we have done an example of how the this antenna control system can be converted into this block diagram by using the transfer function. Hope you can we can do. We can discuss other. We can move forward other lecture in the next lecture, in which we can discuss some other aspects of this control system. Thank you.